Methods in Measurement Lecture, version 2017-07-12, Section 2, Using Scientific Measurements. The objective of this lesson are first to distinguish between accuracy and precision, to determine the number of significant figures in a measurement, to perform mathematical operations involving significant figures, converting measurements into scientific notation. Actually, this one here is going to be a separate packet that you'll get in my lecture class. And then distinguishing between inversely and directly proportional relationships. These are the things that you should be able to do, the skills that you should be able to master in this session. All right, accuracy and precision. Two words that seem like they mean the same thing in everyday language, but to a chemist they mean very different things. Related, but different. Okay, accuracy refers to the closeness of measurements to the correct or accepted value. In science, we've measured certain things over and over again, and every scientist agrees that these numbers are the accepted value. For example, the density of water at a particular temperature is known to be a certain number. If you were to go into the lab and measure the water at that temperature for yourself, how close you are to that accepted value is how accurate you are. Precision, however, refers to the closeness of a set of measurements of the same quantity made in the same way. So precision refers to if you took those measurements multiple times and they were close to each other, or how close they are to each other would determine how precise you were. It has nothing to do with what the accepted value is. It has to do with how close measurements are to each other. All right, here's a classical analogy that we use to describe accuracy and precision. We have a dartboard. The bullseye of the dartboard is the accepted value, and the darts are the measurements. So if the darts hit the bullseye, we'd say they're accurate. So here we have 4 measurements that are all accurate. Now, how close the darts are to each other describes their precision. And say these 4 darts in the first diagram are also precise, besides being accurate, because they're close to each other. Look at the next diagram, letter B. These darts are close to each other, so you would say that they're precise. However, they're not accurate because they're not on the bullseye. All right, in the next diagram C, you'd see you have the darts are far apart, so they're not precise. They're also not at the bullseye, so they're not accurate either. Okay, taking a look, this is a triple beam balance that you would use in a classroom, and what you can't see over here to the side would be the pan where you put the chemical on there, and then if you want to find the mass of that chemical, there's 2 ways you could use this balance. One is to take a chemical sample and find its mass, and the other way is to find a particular mass, like so many grams, weigh out so many grams. In this case, we're measuring the mass of an unknown quantity of salt. We're actually going to do this lab later on in the lab session. So, how would you record the measure of this mass of salt? You would write down 5. You look at this slider. You'd be sliding these sliders over until these 2 lines line up at 0. And that's when you know that the mass represented by these weights are the same as the mass on the pan of the balance. So you would write this down as 5 point. Now to see what is next, we have to enlarge this section. And this line here represents 5.8. So we're sure it's more than 5.8, but not as much as 5.9, so you'd write down 5.8. Now if it was this line here represents 5.81, 5.82 here, 5.83 here, 5.84, so it's more than 5.84, but not as much as 5.85, so you'd write down 5.84. Now, when we measure things in chemistry, we're supposed to write down all the numbers that we know for sure. And any scientist measuring this would write down these first 3 numbers if they knew what they were doing. The last digit we're supposed to make an estimation or a guess. That's the way we measure stuff in science. So if you guess that this is halfway between 5.84 and 5.85, then you might write, or you should write, 5.845. Now, notice, because this last digit is a guess, you might have written down 5.844 or even 5.846. And we've decided we're not going to argue about that. That since that last number is supposed to be an estimation anyway, the only way we would solve an argument like that would be to get a better balance. So that's our standard operating procedure, to write down all the numbers you know for sure and the one estimation. And this relates to the precision of this balance. Actually, this number's not correct yet. Do you know why? You can pause this if you want. The answer is it's not correct in chemistry unless you have a units associated with it. So it'd be 5.845 grams. That's an important thing in this course. If you take a quiz for me and you write down 5.845, I'm going to mark it wrong, because it's 5.845 grams. Okay, here's another example. We have a dartboard, and these darts are far apart, so they're not precise, but they are accurate. How could that be? How could they be not precise but accurate? Well, it turns out that the average of these four measurements is the accepted value, or would line up with the bullseye. Okay, so let's put this knowledge to practice here. If the accepted value is 5.6789 grams, and what could you conclude about these measurements? 5.2223, 5.2224, or 2223? Well, think about the balance that were used. In this course, if I ask you to compare precision, your frame of reference is the triple beam balance. Frame of reference is important. So remember, when we measured something with the triple beam balance, we had the first decimal point. We expect that to be the same, the second decimal point to be the same, and the third was our estimation here. So if we're determining that these numbers are precise, then the first two decimal points should be the same. And look, 5.22, 5.22, 5.22, and the next one could be the same or could be different. So according to this criteria, how would you finish this sentence? They have blank precision and blank accuracy. Pause. You'd say they have good precision but poor accuracy, because even they're very close to each other, but they're not close to the accepted value. Now, a little bit about frame of reference. It wouldn't be fair if I were to ask this question without giving you the frame of reference of the triple beam balance. In terms of precision, the frame of reference is very important. For example, if you were putting a rocket on Mars, and you could put that rocket on Mars with a precision of 1 meter from where you said you were going to put it, then that would be extremely precise in that context. However, let's take that same concept and apply it to your dentist. If you said the precision of your dentist of getting the tooth that needs to be replaced in your mouth, his precision was within 1 meter, that would not be precise at all. Who knows where that tooth would end up? All right? So frame of reference. If someone asks you if numbers are precise, ask them for a frame of reference. Okay, how about this example? The accepted value is unknown. What can you conclude about these numbers? 7.4546, 7.4353, 7.4301. Comparing that to the triple beam balance, you would expect the first numbers to be first decimal to be the same, and they are, and the next one to be the same, and they're not. This is a 5, that's a 3. Now there's another 3. So how would you fill in the blanks here? Pause. You would say they have poor precision because they're not as close as you would expect them to be for a scientist using a triple beam balance, and their accuracy is unknown because you don't know what the accepted value is, so you can't say anything about the accuracy. Okay, what can you conclude about these values? Let's take a look at this example. If the accepted value is 7.4540 grams, and these are your measurements, finish this sentence. Alright, you'd say their precision is good and their accuracy is good. Because look, the first decimal place is 444, the next one is 555, the next one is 4, 4, and 4. So yeah, they're very precise. Even these 4s could be even a different number and you'd still say they were precise, because that's the limits of the balance. And they're very close to the accepted value. Okay, so back to our triple beam balance. This measurement here of 5.845 illustrates the precision of this balance. You would expect that two people who were equally qualified using the same balance would be able to measure things within the same level of precision. They'd get the 5 the same, the 8 the same, the 4 the same, and this last digit here could be a guess. Alright, mass determination lab. In the lab section of this course, if I'm your instructor, you would take you would actually do this lab. So we're going to do it virtually. So in this lab, imagine that at the lab table there is a balance at 7 different lab tables, and there's a sample, a little vial of salt on each lab table. So each lab group would measure out this salt, but each student would do it independently. So we'd start the lab with a person from your lab group would go and measure the sample and alone, without everybody there, and then they'd write down the number and they'd sit down in their seat and they wouldn't share the number with anybody. And then they would tag the next lab person. They would go up until eventually everybody in your lab group weighed the same sample without communicating. Then once that was done, then you'd communicate and you'd fill out the lab. And if you have this document, which you can get in the classroom, then you can go along and fill in the document, or you could fill in the PowerPoint somewhere. All right, so here's some important information you need to know. You need to know the mass of the empty vial and the cap. Does anyone know why? Well, you measured the vial with the salt inside and the cap, and you want the measurement of just the salt. So the number you wrote down on your sheet includes the empty vial and the cap and the salt. So you'd have to subtract the mass of the empty vial and the cap, which was determined for you, depending on which lab station you went to. Okay, so here's the lab report. You have 3 students in this sample lab, and they all got their independent measurements. So the first student got 5.846 grams, the second got 5.845, and the third got 5.844. You could see in terms of precision that these are pretty good measurements. And next, question F, you'd calculate the average value. So you can pause the tape and calculate the average value. When you come back, we'll tell you the answer. The average of these numbers is 5.845. You get that by adding up all 3 numbers and dividing by 3. All right, question G, how close is the largest measurement from this average? We'll take a look. The average is 5.845. The largest number is 5.846. So if you find the difference between these 2 numbers, you'd see the average is, the difference is 0.001 grams positive. In other words, the largest number was that much greater than the average. Question H, how close is the smallest measurement from the average? Well, smallest measurement, if you find the difference between these 2 numbers here and here, you'd see that it's minus 0.001. So it could be less by 0.001 grams. Now, why do we do this? We do this to illustrate the concept of precision. So measuring the precision of these measurements, or the precision of this balance, looking at these values, you would say the precision is plus or minus 0.001 grams, meaning that you're confident that this balance could be precise within this range of plus or minus 0.001 grams. Okay, so there's your balance, there's your measurements. 3 people getting the same measurements in the first 3 digits, and the third digit is the estimate. This illustrates the concept of precision as well as how we measure things in the chemistry lab. Okay, let's continue with the lab report. We've already calculated F and I, the average and the precision for the instrument. So let's answer question K. If 3 other students were to weigh your sample, what measurements would you accept as a valid measurement? Let's rephrase this question. Suppose someone in your lab group transferred into another school and you needed to recruit somebody for your lab group. So you decided you're going to interview people because you don't want somebody that doesn't know their chemistry or doesn't know how to use their balances. This is the middle of the year. Your midterm grade depends upon a practicum lab that you're going to do as a group, hypothetically. And so you want to make sure you get a quality person to replace the person that left. So one of the things you might do is give them that sample that 3 of you weighed previously and see if they come up with a number that's close enough to yours. If they do, great, they're in. If they don't, you really don't want that person in your lab group. So I'm asking you to invent 3 numbers that would be acceptable for this new lab person. If they got this number, you'd say yes, they're in. So 5.844 would certainly be acceptable. 5.845, even 5.846. I mean, you might take a 5.843 or 5.847. All right, hopefully you got the idea. This is how precise you would want your lab partners to be in getting the measurements. All right, now error. There's always some error in a measurement. There's no perfect measurement because there's no perfect balance to measure things to an infinite number of decimal places. So where does error come from? Well, it could come from the skill of the measurer, as we illustrated in the previous example. It could come from the conditions of the measurement. Sometimes in this class we run a Pine Barrens lab field trip where we go out into the Pine Barrens and we measure the different chemicals in the water, and we bring balances with us. If the conditions are windy or rainy or sandy, you don't get good measurements, the same that you would get back in the laboratory. So the conditions of the measurement are important. Also the measuring instruments. More expensive, better instruments are usually more expensive. So the quality of your instruments determines also how good you can measure things out. Alright, new topic, significant figures. Now this is related, as you'll see, to our precision discussion. Alright, significant figures. Here's a definition for significant figures. It's important that you understand this concept. In a measurement, significant figures in a measurement consist of all the digits known with certainty plus one final digit which is somewhat uncertain or is estimated. Sound familiar? The measurements we've been taking represent digits we knew were correct on the balance and one that was estimated. Okay, notice here the term significant does not mean certain, because the significant figures include the certain ones and the one uncertain or estimated one. All right, to show you how important this is a description of a standardized test, formerly called the HESPA test, and in the sample student booklet it gives a chemistry question on significant figures. Now I know you can't answer this right now, but that's not important. The important thing is that you know that this is important concept, skill for you to be able to master. Alright, so let's apply this into a real life situation. Suppose you're measuring the length of a nail in a class, and you're using this ruler here. If you look closely, now these are centimeters, 0, 1, 2, 3 centimeters. So you record this measurement as 6 would be the first place, and this is 6.1, 6.2, 6.3, so it's more than 6.3 but less than 6.4, so you'd write down 6.3. If you thought it was halfway there, you'd write it as 6.34. You might say, or 6.35, you might say 6.34 or 6.36. That would be acceptable. The point being that you write down the numbers you know for sure, the 6 and the 3 and the 1 estimation. So this number here has 3 significant figures in this measurement. Okay. In science, it's important for us to be able to work with significant figures. And if a scientist wrote down the number correctly, knew what they were doing in the lab, all of the non-zero digits we can assume to be significant. And so if it's not zero, if it's a non-zero digit, meaning 1, 2, 3, 4, 5, 6, 7, 8, or 9, then you know it's significant. It's the zeros that are a little bit difficult to work with. So we have a set of rules for determining the number of significant figures that relate to zeros. These rules need to be understood completely. You need to be able to work with these rules. So I'm going to ask you to memorize these rules, and when we meet, anytime after this video was assigned, you're expected to be able to come to class and write down these rules from memory. So memorize them right now and be prepared for a quiz. Alright, so let's explain these rules. Rule number 1, zeros appearing between non-zero digits are significant. So, if you have a number like 40.7, it has 3 significant figures. This is called a captive zero. It's a zero between 2 non-zero digits, and it's considered significant. Likewise, in this measurement here, 87,009 kilometers, these 2 zeros are significant, so this measurement has 5 significant figures. All right, rule number 2. Zeros appearing in front of all non-zero digits are not significant. So we call these leading zeros. So numbers such as 0.095897, these zeros, these leading zeros, are not counted. So this measurement here has only 1, 2, 3, 4, 5 significant figures. All right, in this example here, 0.0009, there's only 1 significant figure. These leading zeros, leadings are meaning that the numbers starting with 0, going from left to right. All right, so that only has 1 significant figure. Right, rule 3, zeros at the end of a number and to the right of a decimal point are significant. So if they're at the end of the number and they're to the right of the decimal point, that's important. They have to be both. Then you would count them. So this measurement here, 85.00 grams, has 4 significant figures, and this number 9.000009 zeros has 10 significant figures, because all those zeros count and the 9 counts. Alright, zeros that are at the end of a number but to the left of the decimal point can be a little bit confusing. Let's take a look at these 2 numbers. We've got this measurement here, 2,000 meters. That has 1 significant figure. This number here, 2,000 decimal point, 2000 point meters, this has 4 significant figures. I'm going to pause this while you try and figure out what the difference is between the 2. All right. Hopefully you realized that the difference is the decimal point. If we have a decimal point in a number, then it has 4 significant figures. If it doesn't have the decimal point, then you don't count those zeros and it only has 1 significant figure. Okay, let's take a look at an example problem. How many significant figures are in each of the following measurements? So we have 28.6 grams. Well, I'll pause this while you answer it. All right, there are 3 significant figures in this measurement. The 2, the 8, the 6, they're all non-zero digits, they all count. How about the next one? 3440 decimal point centimeters. I'll pause. All right, this has 4 significant figures. This 0 counts because the decimal point's there. How about this measurement here? 910 meters. Well, this has 2 significant figures. This 0 does not count because unlike the measurement above it, there's no decimal point. So So the 9 counts and the 1 counts. The 0 does not count in this case. How about this number here? 0.04604. Pause if you want. Write down your answer. Alright. This has 4 significant figures. The 4 counts, the 6 counts, the other 4 counts, and the 0 counts because it's a captive 0. Okay, so add this to your notes if it's not there already. The 0's to the right of the decimal point, but before the first non-zero digit, in numbers such as 0.07 are not significant. Those zeros are not significant. They're important. They're placeholders. They show the decimal place of the first digit. Without them, they'd be wrong, but they're not considered significant. Okay, can you fill in the blank? Hopefully you realize this is the same as the slide above it. Zeros to the right of the decimal point, but before the first non-zero digit in numbers such as 0.07 are not significant. Okay, more practice. Let's take a look at this. 0.006700 kilograms. All right. Write down your answer. Pause. Okay, according to this, remember these leading zeros do not count, but these ending zeros over here on this side, at the end of the number and to the right of the decimal, you count those zeros. So this has 1, 2, 3, 4, 5 significant figures. All right, let's get back to our lab. Question J says how many significant figures are in your measurement. So let's take a look at these measurements and the average and count the number of significant figures. And write your answer here. Alright, the answer is 4. The 5 counts, the 8 counts, the 4 counts, and the last estimated digit also counts. So there are 4 significant figures. Okay, new example. 0.0067000. This looks very familiar, doesn't it? It has 5 significant figures. Alright. For some reason, the PowerPoint went backwards. Okay, so here's where we should be. Alright, apologize for that. So, if 3 students were doing this measurement, you could expect 3 values that were slightly different by the last digit, by the thousandth place. That's how we measure things in chemistry. This illustrates the precision of the instrument as well as how we do measurements in chemistry lab. Okay, rounding. When we need to round, we're going to do the 5 and up rule. So if you need to round to so many digits, you're going to look at that last digit and you're going to decide if you're going to round that last digit up or keep it the same. And you do that by looking at the digit next to the digits you're going to round. When I say next, I mean to the right of. And if that number is 5 or greater, you round up. If it's less than 5, then you round down. Or keep the digit the same. Okay. So here's some examples. The measurement of 0.045550 grams rounded to 2 significant figures would be, write down your answer. Answer would be 0.046 grams. You're rounding to 2 significant figures, so ignore the zeros, they don't count. You want to keep the 4, that's your first significant figure, and then you're going to keep this decimal place here. But the question is, do you keep it 5 or do you round it up to 6? Well, look over to your right. There's a 5 there, so that means you round that to 6. So the correct answer is 0.046 grams. Okay, I have a video to share with you right off of ABC News.
Label on food may not tell you the full truth about trans fats. A new study in the American Journal of Health Promotion found the Food and Drug Administration does not make food companies list trans fats if it is less than 0.5 gram in a serving size. but a serving size may be less than people normally eat. For example, a serving of potato chips is technically considered just 5 chips. That is less than a gram of trans fats. But many people eat much more than that in a serving, so even though the package label says 0 trans fats, they're actually probably consuming them. The study calls for more precise labeling.
The Delaware and Lehigh Valleys are going green.
Okay, this video obviously relates to rounding and precision that we're studying in class. So let's take a look at a sample question. Could you answer this quiz? How many grams of trans fats would you eat if you ate 50 potato chips? And I could eat 50 potato chips in this setting. I bet most of you could. According to the label, a serving size has 0 trans fats. So if I eat 50, am I having no trans fats? All right, but in fact, a serving has 0.45 grams, and according to the law, they're allowed to say 0 if it's less than half a gram. So let's do the math here. I'll pause the tape if you want to do the math yourself, see if you can figure this out, then we'll come back, we'll give you the answer. Alright, you have 50 chips, which since a serving size is 5, that means you had 10 servings. Each serving was 0.45 grams, so where the label might lead you to believe you had 0 trans fat, you actually ate 4.5 grams of fat, trans fat. Okay, now, in chemistry, as well as in the real world, we take measurements and we combine them. We find averages, we add them, we divide, we multiply, we subtract. When we do these things, you have to be very careful that we don't mess up the precision or the significant figures of our measurements. All right. For example, suppose we're prescribed a medication of 1 gram, and your pharmacist would weigh it out accurately to a milligram worth, so their balance would weigh 1.000 grams. And then you went back to the doctor a couple weeks later and said, hey, you're getting better, so I want to reduce the dose by 1/3. So take 1/3 as much. Now, if you do the math, 1 gram divided by 3, your calculator is going to read 0.333333, infinitely repeating. Does that mean your pharmacist now has to go out and buy a balance, or the drug company has to measure that chemical to millions of decimal places? No. Here's an example where mathematics has given you a number that's more precise than the reality of a situation. Alright, so it's very important that we follow our rules for significant figures when we're mathematically manipulating numbers. So when we're adding or subtracting decimals, the answer must have the same number of digits to the right of the decimal point as there are in the measurements having the fewest digits to the right of the decimal point. When we're multiplying, and we'll do some examples in the next slide, when we're multiplying or dividing with significant figures, then you go by the least number of significant figures. So for multiplication or division, the answer can have no more significant figures than are in the measurement with the fewest number of significant figures. So addition or subtraction, you go by the fewest digits to the right of the decimal point, and multiplication or in division, you go by the fewest number of significant figures. Alright, so when adding numbers, the sum should be rounded so the final digit is in the same place as the leftmost digit of the numbers added. So what does that mean, leftmost digit? Well, here we have 3 measurements. The first number has a leftmost digit over here. The second number has a more leftmost digit. This is more to the left than the 2. So when you're adding numbers, the sum is rounded so the final digit in your answer is in the same place as the leftmost digit of the numbers added. So compare these numbers. The ones that are added, this measurement has the leftmost decimal place here. So you'd round to this place, the 10th place. So if you're adding these numbers, you get 30.123 on your calculator, but you should round that to 30.1. That's what we mean by leftmost most. Little confusing there, but hopefully this example will illustrate it for you. Okay, so let's practice this. Using a metric ruler with 1 millimeter divisions, the side of a rectangular piece of wood was measured to be 6.59 centimeters and 2.35 centimeters, which corresponds to an area of 15.4865. In other words, cubic square centimeters squared. That should be a superscript. All right, so to find the area of this piece of plywood, you'd multiply the length times the width, and your calculator would give you this big number here. But that it would not be the right answer, because when you multiply numbers, measurements in particular in chemistry, you can only write down an answer to the least number of significant figures in your data. So this data point has 3 significant figures, this data point has 3 significant figures. Your answer has to be rounded to 3 significant figures. So the correct answer would be 15.5 square centimeters. Okay, another sample problem. The dimensions of a rectangular solid are measured as such. Calculate the volume. Well, to calculate the volume, you'd multiply the length times the width times the height, and you get this number here. But what is the right answer? I'm going to pause this while you write down the right answer. The right answer would be 8.3 cubic centimeters, because you have to go by the least number. This has 3 significant figures, this has 2, and this has 2, so you got to go with 2 significant figures in your answer. Okay. So let's do some practice here. Carry out the following calculations. Express each answer to the correct number of significant figures. So, pause. Your calculator would say 2.8297, but you would round that to 2.83, the 3 significant figures, meters. How about this one here? Pause. Okay, when you take 2.4 grams per milliliter and multiply it by 15.82 milliliters, you get 38 grams, which would be your correct answer because you want to round it to 2 significant figures. Okay, now a word about conversion factors. When we involve conversion factors in our calculations, we're going to say that conversion factors have an infinite number of significant figures. For example, there are 12 inches in a foot. They're exactly 12 inches in a foot, not 12.00. It has an infinite number of significant figures. Okay, new topic, percentage error. How wrong is a measurement? That's what you're measuring, the error, the percentage of your error. So say a student is measuring a sample in the chem lab and they got it to be 105 grams when the accepted value was 100 grams. So how far off are they? Well, they're 5 grams off, positive 5 grams off. So to calculate their percentage error, it would be 5%. Using this value, the experimental value minus the accepted value divided by the accepted value times 100. So what about if the measurement was 95 grams and the real or accepted value is 100 again? Well, they're off by minus 5 grams. So calculating out their percentage, it would be minus 5%. The experimental value of 95 grams in red, this is all color-coded, minus the accepted value of 100. The answer to that you would divide by the accepted value of 100 grams and multiply that by 100. So the answer would be minus 5%. Okay, a student measures the mass of a volume of a substance and calculates its density at 1.4 grams per milliliter. The correct or accepted value of the density is 1.3. Calculate their percentage error. So we'll pause here. Alright, the percentage error would be 7.69%. They would use this formula. The percentage error would be the experimental value, which was 1.4 grams right here in the question. So we take that number, 1.4 grams per milliliter, minus the accepted value, which was given here, 1.3 grams per milliliter. And you take the answer to that and divide it by the accepted value, which again is 1.30 grams per milliliter. Then multiply that by 100. So if you actually did this on the calculator, you'd get this huge number here, but you need to round it to 3 significant figures according to our rules for significant figures. Okay, back to the lab here. Suppose, let's answer this question here. Another student measures the mass of a different sample and found it to be 111 grams when the accepted value of the sample is 100 grams. Calculate the percentage error. Well, the experimental value is 111, that's in red. The accepted value is 100, so you calculate the percentage error by taking 111 minus 100 grams, then divide that answer by 100, multiply by 100, the answer would be 11%, positive 11%. All right, let's look at another question. The accepted value for your sample is listed on line B above. So in the lab, if you actually did this lab, you would look at your measurements of the vial of salt and you'd compare your average value to the accepted value, which I would give you in a chart to calculate here, this answer here for your accepted value. So these are the accepted values of the salt alone, and you would use this to calculate your percentage error in our lab report. Okay. If we actually did the lab in class, then it would be due the class after that. This is a virtual lab, so I'm not going to ask you to turn this one in. Okay, percentage yield. How right is a measurement? All right, so if you're producing a chemical in the lab, and you say you make 95 grams, and theoretically, if it were perfect conditions, you'd make 100 grams, then how right are you? What's your percentage yield? Is how close you are to being perfect. Well, this one's really like a test. If you had 100 questions on a test and you got 95 right, you could figure out your grade. All right, 95 out of 100 would be 95%, and you'd use this formula here. The percentage yield, or your grade, would be the actual value, which was 95, divided by the theoretical value, which is in blue here, is 100, times 100, so that'd be 95%. Now, theoretical yield is the maximum possible yield that you could obtain in a chemical reaction. The actual yield is what actually happens when you try to do it in the laboratory. And the percentage yield is a ratio of those two numbers multiplied by 100%. Now, when do we use percentage yield? Well, we're interested in the efficiency of a chemical experiment. So I want you to imagine for a second that you pass chemistry class and then graduate high school, go to college, become a chemistry major, get a job working for a very lucrative chemical company, and you're making mega bucks. And one of the things that you'd be doing there would be to calculate the efficiency of their chemical reactions. And why would they pay you mega bucks? Because in getting the more precise, the more efficient your chemical reaction is, the more money that chemical company is going to make, and the less waste that they're going to have. And if your percentage yield is equal to 100%, which is very hard to get, then the actual yield is equal to the theoretical yield. In reality, in most chemical reactions, the actual chemical produced is less than the theoretical yield. Okay, so here's an example of using that. Suppose we ask you to calculate the percentage yield where a student in a laboratory produced 10.59 grams of a chemical, and theoretically they could have made 11.688 grams. To calculate the percentage yield, you take their actual yield in red here, divided by the theoretical yield in blue, and multiply times 100. So it would be 10.519 grams divided by 11.688 grams times 100 would give you 89 point, well, you'd round that to 5 significant figures. According to your data, it would be 89.998%. All right, the theoretical yield for a 0.1 mole sample of sodium chloride expressed to 4 significant figures is 5.844 grams. Calculate your percentage yield using this theoretical value and your average value. This is a section from a lab that we're actually going to do in class. We're going to weigh out a tenth of a mole. Now, I know we haven't talked about moles yet, but we will later on. So we'll come back to this one. Don't worry about it now. Okay, that's the end of section 2, Methods in Measurement lecture.